Hello there. Welcome back to Midnight Ocean. I'm Velen, your guide to traveling through the wonders of the ocean. Tonight, we're going to discover why the ocean is, or would be, literally Earth's final boss. After all, we've already explored and know so much about our planet, but the ocean depths we know little about. The immensity and mysteries of the oceans intrigue us even today. If these cozy moments calm you, I invite you to subscribe, share a comment, or leave a like. Now, get comfortable, take a deep breath. Don't be afraid, you're safe here. Let's dive deep into the sea and let our imagination guide us to a peaceful and deep night. At 3,800 meters below the surface, where the Titanic rests on the floor of the North Atlantic, the water pressure on any structure is roughly 380 times the atmospheric pressure at sea level. On June 18, 2023, the submersible Titan, operated by the company OceanGate, imploded while descending toward that depth. The Titan imploded under that extreme pressure, approximately 38 MPa or 5,500 psi, resulting in the near-instantaneous death of all 5 people on board, including OceanGate CEO Stockton Rush. Simulations developed in 2023 suggest that, due to the immense pressure, over 330 atmospheres, the hull implosion likely took only a few milliseconds, fast enough to kill the occupants before they even became aware of what was happening. The U.S. Coast Guard's final report, released in August 2025, concluded that the implosion was a preventable tragedy caused by an inadequate design and testing process, no meaningful analysis of the hull's carbon fiber material, and over-reliance on OceanGate's real-time monitoring system to assess hull conditions. At Challenger Deep, the deepest point in the Mariana Trench at 10,935 meters, the pressure reaches 1,086 bar, approximately 1,071 times atmospheric pressure at sea level, or 8 tons per square inch. The Titan imploded at less than 1/3 of that depth. Picture holding an empty soda can and squeezing it with both hands as hard as you can. It gives dents, collapses, but slowly. Now imagine multiplying that force by thousands, applying it from every direction at once in a fraction of a second. That's how an underwater implosion works. The hull doesn't tear or gradually buckle. It collapses instantaneously because the external pressure overwhelms the structural resistance before any movement can even be detected. For the people inside the Titan, there was no warning signal, no sound, no sense of danger. The outside of the submersible simply ceased to exist while the inside still did, for just a few milliseconds. Atmospheric pressure at sea level, the weight of the column of air above us, equals approximately 1 bar, or 101,325 pascals. That value sets the baseline. For every 10 meters of ocean depth, another bar is added, equivalent to the weight of the water column above. At 100 meters, the pressure is already 11 times greater than at the surface. At 1,000 meters, it reaches 100 times. At the 3,800 meters where the Titanic rests, it exceeds 380 times. That increases linear, but its effects on materials are devastating. Metals deform, glass implodes, seals fail, cavities compress. The physics is relentless and doesn't negotiate with rushed engineering. The Titan was built with a cylindrical carbon fiber hull, a material widely used in aviation, but barely tested for repeated pressurization and depressurization cycles at extreme depths. Carbon fiber is extraordinarily strong under tension, forces that pull the material apart. However, hydrostatic pressure doesn't pull. It compresses from every direction. This type of loading, called hydrostatic compression, produces failure modes that are completely different from what carbon composites are optimized for. Experts repeatedly warned that the carbon fiber used in the hull could fracture under deep sea pressure. Each dive imposed invisible, cumulative microcracks, until the threshold of structural integrity was crossed without warning. Submersibles certified by independent bodies go through strict protocols, pressure testing in hyperbaric chambers before any crewed dive, inspection of every joint, every weld, every structural component, operating limits defined with conservative safety margins. OceanGate chose to operate outside that certification system, arguing that excessive regulation would stifle innovation. The findings of the final report attributed the primary contributing factors to the company's inadequate design, certification, maintenance, and inspection process for the Titan. The outcome showed that safety margins aren't obstacles to innovation. They're the minimum cost of operating in environments that don't forgive mistakes. The implosion was not an explosion. That distinction matters physically. An explosion releases energy from the inside out, creating an outward pressure wave. An implosion is the opposite. External pressure greater than internal pressure collapses the structure inward. In the Titan's case, the surrounding water, at 380 atmospheres, rushed into the internal volume at supersonic speed the moment the hull gave way. The pressure differential between the interior, held at normal atmospheric pressure, and the exterior generated a fluid flow so violent that it destroyed everything instantaneously. No biological structure survives that event. Death was so fast that it doesn't even constitute measurable suffering, though that does nothing to diminish the magnitude of the engineering failure that caused it. Comparing depths helps put the scale in perspective. The Mariana Trench, with its 10,935 meters at Challenger Deep, would exert pressure exceeding 1,100 atmospheres on any structure. The Titan imploded at roughly one-third of that depth. That means the deepest point in the ocean would exert 3 times the pressure that destroyed the submersible. Only 3 vehicles have ever reached Challenger Deep with humans on board. The Trieste in 1960, the Deep Sea Challenger in 2012, and the Limiting Factor in 2019. All were designed with solid titanium spheres. Spherical geometry distributes pressure uniformly, eliminating the stress concentration points that cylinders inevitably create. Surviving extreme depths requires the right geometry, the right materials, and adequate safety margins. The Bathyscaphe Trieste, which reached Challenger Deep in 1960, used a simple reinforced steel sphere. Rudimentary technology compared to the Titan's carbon fiber, but geometrically superior for that environment. The sphere is the only shape that distributes hydrostatic pressure perfectly and uniformly across its entire surface. No stress concentration zones, no weak points imposed by geometry. Cylinders have end caps that require structural transitions. Those transitions become preferred failure points under extreme compression. The Coast Guard report also identified a failure in the acoustic monitoring system OceanGate was using as a substitute for formal certification. The system measured acoustic emissions from the hull, sounds generated by propagating microcracks, to detect deterioration in real time. The concept has scientific merit, but the interpretation of the data was inadequate. Warning signals were underestimated or dismissed in dives prior to the disaster. The report concluded that Stockton Rush exhibited negligence that contributed to the deaths and created a false impression about the submersible's safety. Overconfidence in monitoring replaced structural verification, with irreversible consequences. The deep ocean remains fundamentally hostile to pressurized structures. That hostility won't lessen with better technology. It is an intrinsic property of the physics of water under pressure. What technology changes is the ability to operate with adequate safety margins within that hostility. Every additional atmosphere of depth imposes increasing structural demands. Every new mission requires rigorous integrity verification. The Titan tragedy didn't show that deep-sea exploration is impossible. It showed that it is uncompromisingly demanding. No conviction about innovation, no confidence in real-time monitoring, replaces the methodical process of certifying that a structure will withstand, with a safe margin, the forces that the abyss imposes. The ocean that destroyed the Titan in milliseconds remains, for the most part, invisible to science. Only 26% of the ocean floor had been mapped in high resolution as of 2024. The remaining 74% of the floor of the planet's largest habitat is less known than the surface of the Moon, which has been mapped almost entirely. There are underwater mountain ranges larger than the Andes that have never been directly explored. There are trenches that have been visited by humans fewer than 10 times in history. The environment that covers 71% of the planet, that regulates the global climate, that absorbs 25% of human CO2 and 90% of the excess heat from the atmosphere, remains across 3/4 of its physical extent territory that humanity has never seen. And every new expedition that attempts to observe that territory faces the same conditions that destroyed the Titan: increasing pressure, near-zero temperatures, and the total absence of light. Mapping the ocean floor isn't photography. It's measuring depth with enough precision to reveal structures. The primary instrument is the multi-beam echo sounder. Transducers emit fans of sound pulses that travel down through the water column, reflect off the bottom, and return to the ship with travel times proportional to depth. Each pass of a ship produces a mapped strip whose width depends on the local depth. In shallow waters, strips are narrow. In 5,000-meter abysses, each pass covers dozens of kilometers in width, but ships are slow and oceans are vast. In June 2025, the Seabed 2030 project announced that 27.3% of the ocean floor had been mapped to modern standards, with more than 4 million square kilometers of new data added in the past year. A frequently repeated observation is that we know more about the surface of Mars than about the floor of Earth's oceans. Mars was mapped by orbital satellites operating in a vacuum with no obstacles. Light or radar travels through space easily. The ocean blocks electromagnetic waves. Visible light penetrates only a few tens of meters before being completely absorbed. Radar doesn't travel through salt water. Only sound propagates efficiently through the ocean column, hence the dependence on sonar. Satellites can infer rough submarine topography by measuring variations in ocean surface height caused by the gravitational pull of underwater structures. But the resulting resolution is insufficient to reveal features smaller than several kilometers. The scale of the problem requires context. To map the rest of the oceans with high-resolution multi-beam sonar, ships would need to cover distances equivalent to hundreds of times the circumference of the Earth aboard specialized vessels. Even if the entire global fleet of oceanographic ships operated simultaneously, decades would be needed to complete the survey using conventional acoustic methods alone. The Seabed 2030 project, a collaborative initiative between the Nippon Foundation and JEBCO, aims to compile all available data into a publicly accessible map. But the current pace of mapping reveals that completing the task by 2030 will be a formidable challenge. The discoveries made during this effort show that ignorance carries a concrete cost. Off the coasts of Central and South America, researchers found 4 underwater mountains in January 2024, including a massive one standing 2,681 meters tall, covering 450 square kilometers, located at 1,150 meters of depth. That mountain existed without any formal scientific record. It could be home to unique ecosystems, affect local ocean currents, or pose a risk to submarine navigation, and no one knew. Every newly mapped area systematically reveals unexpected features. Canyons deeper than the Grand Canyon, abyssal plains flatter than any continental surface, hydrothermal fields sustaining unprecedented forms of life. Life in the ocean abyss defies established assumptions about the limits of biology. Hydrothermal vents, cracks in the ocean floor releasing superheated, mineral-rich water, support entire ecosystems without sunlight. The energy base isn't photosynthesis, but chemosynthesis. Bacteria metabolize sulfur compounds to generate energy, sustaining giant tube worms, blind crabs, and octopuses adapted to perpetual darkness. Discovered only in 1977 during an exploratory dive near the Galapagos, these abyssal ecosystems revolutionized biology. How many others are waiting in the unmapped territory? Species potentially useful for medicine, chemical compounds with no terrestrial analogs, biological processes adapted to extreme conditions. All of it remains out of reach as long as the ocean floor stays invisible. Ocean mapping isn't just abstract scientific interest. It has immediate practical implications. Fiber optic submarine cables carry approximately 97% of global intercontinental data traffic. These cables rest on the ocean floor, often in canyons and slopes where turbidity currents, underwater avalanches of sediment, can snap dozens of kilometers of cables simultaneously. Knowing the precise topography allows cables to be routed along safer paths. Likewise, tsunamis generated by submarine landslides or underwater seismic faults propagate differently depending on the seafloor bathymetry. Early warning models need accurate maps to predict wave arrival with enough lead time for evacuation. The race to map the ocean floor has accelerated for reasons that go beyond pure science. Exclusive economic zones, areas extending 200 nautical miles beyond national coastlines where states hold sovereign rights over resources, stretch over poorly understood seafloors. Polymetallic nodules, cobalt deposits, iron-manganese crusts. Mineral resources abundant in certain abyssal regions await viable extraction technology. Before any responsible exploration can occur, it's necessary to know what's there and where. Every mapped square kilometer represents data that will inform decisions with economic, environmental, and geopolitical impact for decades to come. Emerging technologies are pushing mapping beyond the limits of conventional ships. Autonomous underwater vehicles, unmanned robots programmed to follow predefined trajectories close to the seafloor, produce ultra-high-resolution data in areas inaccessible to surface ships. Ocean gliders powered by wave energy or temperature differences cover vast distances with minimal energy consumption, continuously collecting acoustic data. Data from commercial vessels, cargo ships, cruise ships, ferries, can contribute depth readings collected during routine voyages through onboard systems. The Seabed 2030 project draws contributions from more than 185 organizations around the world, each partner adding pieces to the puzzle of a planet that hasn't finished being discovered yet. When the Titan imploded above the Titanic, the incident simultaneously exposed two parallel realities of the deep ocean. It can kill in milliseconds any poorly designed structure, and it remains so unknown that we don't even fully grasp what we're missing by not exploring it. The Titanic wreck, discovered only in 1985 by Robert Ballard after decades of searching, rests in a region of the North Atlantic whose floor had never been mapped in high resolution before that expedition. The discoveries made through the global mapping effort are essential for exploring and managing the last frontier on Earth in a sustainable way. The abyss that destroyed the Titan keeps waiting, vast and silent, holding secrets that only patient instruments and sound engineering will eventually be able to reveal. The ocean is not only lethal to unprotected humans, it is also the reason the Earth remains habitable. The oceans cover approximately 71% of Earth's surface and contain 97% of all the water found on the planet. The Gulf Stream keeps northwestern Europe several degrees warmer than it would otherwise be. The Antarctic Ocean absorbs more CO2 than any other ocean. Ocean currents distribute heat from the tropics to the poles, regulating rainfall patterns across every continent. Research published in 2022 showed that over the past 43 years, the Arctic has warmed nearly 4 times faster than the rest of the planet, and summer sea ice has declined more than 50% since 1979. The mechanism driving that accelerated warming is physical. Every piece of ice that melts exposes a dark surface that absorbs even more heat, which melts more ice. It is estimated that 22% of the world's undiscovered oil and gas reserves lie beneath the Arctic. The same Arctic whose ocean floor holds layers of submarine permafrost that, as they thaw, release methane with a warming power 84 times greater than CO2 over the first 20 years of emission. Before understanding why the ocean regulates the climate, it's necessary to understand what makes water an extraordinary substance. Specific heat, the amount of energy required to raise 1 gram of a substance by 1 degree Celsius, is remarkably high in water, 4.18 joules per gram per degree. Iron, by comparison, requires only 0.45 joules. This means the oceans absorb enormous amounts of energy without warming proportionally. The ocean has absorbed more than 90% of the excess heat generated by climate change since the 1970s. Without that buffering capacity, the atmosphere would have warmed far sooner and to a much greater magnitude. The ocean functions as a planetary thermal stabilizer, dampening variations that, without it, would make Earth's climate radically more unstable and unpredictable. Ocean currents don't move randomly. They follow patterns determined by temperature, salinity, wind, and Earth's rotation. The Gulf Stream carries warm tropical water along the eastern U.S. coast toward the North Atlantic, releasing heat into the atmosphere and making the climate of Western Europe far milder than its latitude would otherwise allow. London sits at the same latitude as parts of Canada where winters are Arctic. The climate contrast is a direct consequence of that current. This circulatory system, called the Atlantic Meridional Overturning Circulation, depends on density differences between warm, shallow water and cold, dense water that sinks in the North Atlantic. Changes in those density differences, caused by ice melt and warming, threaten the stability of the system. The oceans contribute to climate regulation by absorbing more than a quarter of human CO2 emissions and approximately 90% of the excess heat. That absorbed CO2 doesn't simply disappear. It dissolves in the water, forming carbonic acid, which then dissociates and releases hydrogen ions. More hydrogen ions mean greater acidity. Since the Industrial Revolution, the average pH of the ocean has dropped from 8.2 to 8.1, a change that seems small but represents a 26% increase in the concentration of acid ions, given that the pH scale is logarithmic. Organisms that build shells or skeletons out of calcium carbonate, corals, mollusks, certain planktons, face increasing difficulty precipitating those minerals in more acidic water. The base of the ocean food chain is under direct chemical pressure. The Arctic represents the point where multiple pressures converge with the greatest intensity. White sea ice reflects up to 80% of solar radiation, high albedo. Dark exposed ocean absorbs up to 94%, low albedo. When ice melts and exposes water, the albedo difference creates a positive feedback loop. Greater absorption generates more warming, which generates more melting, which generates more absorption. The Arctic has warmed 3 to 4 times faster than the global average. Air and sea temperatures have led to a decline of at least 50% in the extent of Arctic summer sea ice over the past 4 decades. This isn't a theoretical model. It's observed data recorded by satellites since 1979. The ice that remains is thinner and younger, making it more vulnerable to future melting. Below the Arctic Ocean floor, especially on the Siberian and North American continental shelves, there are layers of submarine permafrost. Frozen soil that was covered by advancing seas during past deglaciations. This permafrost trapped beneath Arctic waters currently contains 60 billion tons of methane and 560 billion tons of organic carbon. As long as it stays frozen, it acts as a seal locking in those gases. As the Arctic Ocean warms, that seal progressively thaws. Released methane is particularly concerning because its global warming potential is 84 times greater than CO2 over the first 20 years after emission, before it degrades into CO2 through atmospheric reactions. A rapid, large-scale release would constitute a climate feedback of a magnitude that is difficult to model with precision. Submarine permafrost has been thawing since the end of the last glacial period, about 14,000 years ago, and currently releases approximately 140 million tons of carbon dioxide and 5.3 million tons of methane into the atmosphere per year. That current flow is the result of a natural deglaciation process that began millennia ago. What concerns scientists isn't the current flow, it's the potential acceleration caused by the warming layered on top of the natural process. Climate models carry significant uncertainty regarding the rate of submarine permafrost thaw precisely because this system has been poorly studied. The ignorance about the ocean floor, evidenced by the percentage still unmapped, translates into uncertainty about climate feedbacks that could significantly alter projections of future warming. Ocean currents also transport essential nutrients for biological productivity. Upwelling, the process by which winds push surface water aside and allow cold, nutrient-rich deep water to rise to the surface, fertilizes some of the most productive marine regions on the planet. The coasts of Peru and California, fed by upwelling, support enormous fisheries that feed entire populations. Changes in wind patterns caused by warming could weaken or shift these upwelling systems, affecting both marine ecosystems and human food security. The ocean is not merely a passive climate regulator. It is a dynamic, interconnected system where disturbances in one region propagate to others through pathways that remain only partially understood. According to an assessment by the United States Geological Survey, the Arctic holds an estimated 22% of the world's undiscovered conventional oil and gas resources, including 90 billion barrels of oil and 1,670 trillion cubic feet of natural gas. The geopolitical irony is stark. The thawing caused by warming makes these resources increasingly accessible, creating economic incentive to extract them, which would generate additional emissions that would accelerate the warming that thaws the submarine permafrost that releases the methane that amplifies the warming. Every component of the system feeds back into the others. No single piece can be understood in isolation. Pressure, darkness, and near-zero temperatures destroyed the Titan in milliseconds. Those same conditions that killed 5 people in that submersible are conditions of stability for abyssal ecosystems that have existed for millennia, and for physical processes that regulate the climate of the entire planet. The deep ocean is not just a backdrop for science. It is an active mechanism that determines whether the Earth remains habitable on timescales that transcend any individual human generation. Approximately 91% of the excess heat trapped by greenhouse gases and roughly 30% of human CO2 emissions are stored in the ocean, shielding humanity from even faster changes in the climate. Exploring what remains invisible isn't optional scientific curiosity. It is a prerequisite for understanding the system that sustains life as it exists, before the changes already underway outpace our ability to model or mitigate them with enough precision to guide meaningful collective decisions. In certain regions of the ocean, particularly in the Arabian Sea, the Gulf of Mexico, and stretches of the Eastern Pacific, there is a layer called the oxygen minimum zone, where the concentration of dissolved oxygen is so low that most marine animals cannot survive. In these regions, the decomposition of organic matter has consumed all available oxygen. The Arabian Sea has the thickest oxygen minimum zone in the world. Over the past 50 years, the volume of these zones across the oceans has grown significantly, driven by warming waters. Warm water holds less dissolved oxygen. A diver who unknowingly entered one of these zones would be in water that is chemically incapable of sustaining any form of aerobic metabolism. The problem is not visible, has no smell, has no texture different from the surrounding water. It is a chemical absence that kills without warning. To understand an oxygen minimum zone, you first need to understand how oxygen enters the ocean. It dissolves into the water mainly at the surface, through contact with the atmosphere, and through photosynthesis by algae and phytoplankton living in the sunlit zone. Currents and turbulence carry that oxygen down to deeper layers. In tropical and subtropical zones with strong stratification, however, the warm, light surface water forms a barrier that prevents mixing with the cold, dense water below. The result, the intermediate layer receives descending organic matter, feces, carcasses, debris, that bacteria decompose while consuming oxygen, with no new oxygen arriving to replace what was used. The Arabian Sea sustains the thickest oxygen minimum zone in the open ocean, stretching from approximately 150 to 1,250 meters of depth, a layer over 1,000 meters thick where oxygen concentration is suboxic, below 4 micromoles per liter. For comparison, larger fish and crustaceans require minimum concentrations of between 60 and 120 micromoles per liter to survive. In the Arabian Sea's oxygen minimum zone, that concentration is reduced to less than 1/20th of the minimum required by most animals. This exceptional thickness results from the combination of intense biological productivity at the surface, which generates an enormous amount of descending organic matter, with slow intermediate circulation that doesn't replenish the consumed oxygen. Though invisible from the surface and undetectable by human senses, these zones have profound ecological consequences. Fish, squid, crustaceans, and other aerobic animals do not enter this layer. It acts as an impassable physical barrier determined by chemistry, not walls. Creatures that need to cross it to migrate vertically must do so quickly, with enough oxygen reserves, or they die. But anaerobic organisms, those that don't need oxygen, especially certain bacteria, thrive. These anaerobic bacteria carry out a process called denitrification. In the absence of oxygen, they use nitrate as an alternative oxidant, converting it into nitrogen gas. The Arabian Sea, despite representing less than 2% of the world ocean's area, accounts for up to 40% of global water column denitrification. Denitrification has impacts that go far beyond local chemistry. Nitrate is a fundamental nutrient for phytoplankton, the base of the marine food chain and one of the planet's primary oxygen producers. When anaerobic bacteria convert nitrate into nitrogen gas in oxygen minimum zones, that nitrogen escapes into the atmosphere, becoming unavailable to producing organisms. Oceans with larger oxygen minimum zones show lower nitrate availability, which suppresses biological productivity on a regional scale. A less productive ocean absorbs less CO2, performs less photosynthesis, and sustains less biomass, a feedback loop that connects local deoxygenation to global biogeochemical cycles. Over the past 50 years, the oceans have lost more than 2% of their total oxygen as temperatures have risen. That average figure masks concentration. The greatest losses have occurred precisely in the regions that already had low concentrations. The oxygen minimum zones themselves have expanded in volume. The mechanism is straightforward. Warm water dissolves less gas than cold water, a physical phenomenon called reduced solubility. On top of that, warming intensifies ocean stratification, making the layers more resistant to mixing and reducing the vertical transport of oxygen. The result is twofold. Less oxygen reaches the deep ocean, and what oxygen exists is consumed faster by bacterial metabolism accelerated at higher temperatures. A human diver who accidentally entered a severe oxygen minimum zone would not notice the transition. The surrounding water looks identical. Temperature and pressure change with depth in the expected way. But the dissolved oxygen, which the diver doesn't breathe directly but which determines the viability of the entire surrounding ecosystem, simply isn't there. Animals that migrated away to escape that absent zone don't exist there. The biological silence is total. Any aerobic organism that depended on the external environment for oxygen, as all marine animals do, including those with gills, would progressively perish as the cellular mechanisms of energy production failed from deprivation of the essential oxidant. Coastal dead zones, different from open ocean oxygen minimum zones, but caused by a similar mechanism, occur near river mouths where excess agricultural nutrients trigger massive algal blooms. When those algae die and sink, their bacterial decomposition consumes oxygen from the water column fast enough to create severe hypoxia. The Gulf of Mexico is home to one of these seasonal coastal dead zones, formed by excess nitrogen and phosphorus carried by the Mississippi River. In years with heavy rainfall and large agricultural runoff, this zone can exceed 20,000 square kilometers, an area larger than the state of Connecticut, making the bottom completely uninhabitable for fish and shrimp. The most immediate warning sign of the expansion of oxygen minimum zones is the displacement of fish species. Fish squeezed between the warming surface and the hypoxic zone below become more vulnerable to fishing, more concentrated in narrower depth ranges, and more exposed to mass mortality events when temporary oceanographic disturbances push the hypoxic zone higher. Upwelling ecosystems like that of the Peruvian coast, among the most productive in the world, are already recording impacts on the vertical distribution of anchovies and other commercially critical species. What seems abstract at the ocean scale becomes very real in the fishing economies of populations that depend on the sea as their primary source of protein. The Arabian Sea's oxygen minimum zone, the thickest on the planet, is the product of a particular set of interactions. Monsoons that generate intense surface productivity, slow intermediate circulation, and geographic boundaries that limit ventilation. This system has operated for millennia in an unstable equilibrium. Current warming is adding pressure to that equilibrium, though the future of the Arabian zone is uncertain. Recent measurements between 2019 and 2023 showed surprising oxygenation, attributed to variations in regional circulation. This complexity is precisely what makes the ocean so difficult to model. Systems that respond to multiple simultaneous forces, some amplifying each other, others competing, producing behaviors that defy simplified predictions. In 2019, Victor Vescovo reported finding a plastic bag and candy wrappers at the bottom of Challenger Deep. Most human beings have never come anywhere near 11,000 meters of depth. Only a handful of people in history have made that journey, in specially built submersibles representing decades of engineering. The trash got there first. A study published in 2018 reported the widespread presence of plastic even at depths greater than 6,000 meters, with 92% of that debris coming from single-use products. The study is based on a database of photographs and videos of debris collected since 1983 across 5,010 dive expeditions. The deep ocean, inaccessible, lethal, unexplored across 3/4 of its extent, already has trash scattered across its floor before it has been adequately mapped or understood by science. How does a plastic bag travel 11,000 vertical meters to land at the deepest point on the planet? The journey begins on land, in landfills, on sidewalks, in rivers, in storm drains. Discarded plastic enters waterway systems, is carried by river currents to coastal estuaries, and enters the ocean. At the surface, ocean currents concentrate fragments into gyres, the well-known garbage patches of the North Pacific and Atlantic. But denser plastic colonized by biological organisms that increase its density, or fragments absorbed by marine organisms that later die and sink, begin a gradual descent. Ocean trenches act as drains. Currents converge toward the deepest depressions, dragging suspended material down to the bottom. The 2018 study analyzed 30 years of visual records collected by submarines and remotely operated vehicles belonging to the Japan Agency for Marine Earth Science and Technology. Out of 5,010 cataloged dives, 3,425 items of man-made debris were identified. More than a third was macroplastic. Of that total, 89% corresponded to single-use products, bags, bottles, packaging. At depths greater than 6,000 meters, plastic accounted for more than half of all litter found, and 92% of that plastic was single-use. The deepest item on record was a plastic bag in the Mariana Trench at 10,898 meters. Even before Victor Vescovo personally descended to the same location the following year. Microplastics, fragments smaller than 5 millimeters generated by the breakdown of larger pieces through ultraviolet light and mechanical abrasion, penetrate even deeper and more pervasively than visible plastic. Studies analyzing crustaceans collected from 6 of the deepest ocean trenches, including the Mariana Trench, found microplastics in the digestive tract of every animal examined. Amphipods, crustaceans abundant in the deepest fissures, had accumulated microplastic concentrations higher than those found in crustaceans from far more exposed coastal zones. The explanation is partly the same as for the material flow. Trenches act as collectors, and the filter-feeding organisms living in them process everything that drifts down. The persistence of plastic in the ocean environment is extraordinary. On land, sunlight breaks plastic down into microparticles over the course of decades. On the ocean floor, the absence of ultraviolet light, near-zero temperatures, and extreme pressures create a preserving environment. Plastic deposited in ocean trenches can remain intact for hundreds or thousands of years. This turns the ocean floor into a permanent archive of a specific geological era, the Anthropocene, recording with stratigraphic precision the moment when humans began producing materials that the natural environment has no mechanisms to break down on any relevant timescale. The presence of plastic in Challenger Deep puts the story of human exploration in a particular light. Only 4 expeditions with a human presence reached that depth through 2023. The Trieste in 1960, the Deep Sea Challenger in 2012, the Limiting Factor in 2019, and 1 subsequent expedition. Each required decades of technological development, advanced materials engineering, and million-dollar investments. The plastic, by contrast, arrived without technology, without intent, without any specific investment, carried passively by currents that connect everyday consumer behavior to the most inaccessible abysses on the planet. Amphipods from ocean trenches that accumulate microplastics in their tissues are collected, studied, and reveal something disturbing. Organisms that evolved in extreme isolation, without any contact with human metabolism, already carry chemical markers from synthetic products. Chemical additives from plastic, phthalates, polychlorinated biphenyls, brominated flame retardants, have been detected in the tissues of abyssal crustaceans. These compounds have known endocrine effects in laboratory organisms. Their effects on abyssal ecosystems, where species with slow reproductive cycles and unique metabolic adaptations were shaped by millions of years without these substances, are completely unknown. The sharpest irony in this story is that plastic reached the ocean floor before the ocean floor was mapped. The deepest point on the planet received human garbage before it was adequately documented by the science that aims to understand it. This sequence reverses the expected order of the relationship between humanity and the environment. Normally, exploration precedes impact. In the case of the deep ocean, impact preceded exploration. The science that now tries to study abyssal ecosystems finds environments already altered by decades of artificial material deposition, without ever having documented what they looked like before. Solutions to ocean plastic pollution don't begin in the ocean. They begin on land, at the points of production and disposal. Waste collection systems, regulations on single-use plastics, product design that allows for effective recycling. Each of these interventions reduces the flow at the source. Ocean cleanup technologies, such as floating barriers in rivers before they reach the sea or surface skimming systems, have limited impact. They are ineffective against microplastics dispersed throughout the deep water column and completely powerless against material already deposited in abyssal trenches. The material that reached the bottom of Challenger Deep before any human expedition will remain there for a period that transcends any current political or technological planning horizon. In the open ocean, a tsunami passes under vessels without being noticed. The wave has a wavelength of hundreds of kilometers and an amplitude of only a few centimeters in deep water. A ship in the open ocean during a tsunami feels nothing at all. The danger begins when the wave encounters the shallow floor near the coast. Speed drops, height increases, and the wave can reach 30 meters before it breaks. Tsunamis can travel thousands of kilometers at speeds of up to 800 kilometers per hour. Between 1998 and 2017, tsunamis caused more than 250,000 deaths globally, including more than 227,000 deaths from the 2004 Indian Ocean tsunami. The same event that, in the open ocean, goes completely unnoticed by a passing vessel, becomes a 30-meter wall of water as it reaches the coast, and can keep causing destruction for hours, with crests arriving at intervals of 10 to 45 minutes. The physics of a tsunami begins with the sudden displacement of a large volume of water. Undersea earthquakes along subduction zones, where one tectonic plate dives beneath another, raise or lower the ocean floor within seconds. That vertical shift in the seafloor transfers energy to the entire water column, from surface to bottom. Unlike wind waves, which only move the surface layer, a tsunami mobilizes the full ocean depth simultaneously. This characteristic, a long wavelength wave moving a complete water column, determines its extraordinary properties of speed and energy persistence across thousands of kilometers. In the open ocean at depths of 4 to 5 kilometers, the propagation speed of a tsunami approaches 700 to 800 kilometers per hour, comparable to a commercial jet. Typical wavelengths range between 100 and 500 kilometers, separating crests by continental distances. With that geometry, the amplitude, the difference between the wave's peak and the ocean's mean level, is only a few centimeters to a few decimeters. A ship crossing that tsunami feels an imperceptible disturbance on the surface. Instruments anchored to the ocean floor, known as DARTs, Deep Ocean Assessment and Reporting of Tsunamis, detect the pressure variation caused by the passing wave and transmit the data via satellite to warning centers. What transforms that imperceptible signal into a coastal catastrophe is the shoaling effect. As the wave approaches the coast and the depth decreases, its speed drops proportionally to the square root of the depth. The front of the wave slows down, the back, still in deep water, advances faster. The wave compresses horizontally. Through the conservation of energy, all that kinetic energy from the complete water column has to go somewhere. The horizontal compression converts into vertical rise. An amplitude of 30 centimeters in the open ocean can become a wave of 10, 20, or 30 meters by the time it reaches the shallow coastal floor. The 2004 Indian Ocean tsunami reached heights of more than 30 meters along the northern coast of Sumatra. The earthquake that triggered the 2004 tsunami, magnitude 9.1, with its epicenter 150 kilometers off the coast of Sumatra, was the most powerful recorded in the past 5 decades. The rupture along 1,200 kilometers of subduction zone shifted the ocean floor vertically by several meters along that entire length, generating enough energy to propagate waves across the entire Indian Ocean. The tsunami reached the northern coast of Indonesia within 30 minutes, Sri Lanka and India within 2 to 3 hours, and Somalia, 5,000 kilometers away, hours later. In total, 227,000 people died across 14 countries. Most of the deaths occurred because there was no warning system in the Indian Ocean in 2004. The only operating system was in the Pacific, where tsunamis are more frequent. The coastal dynamics of a tsunami are more complex than a breaking wave. Often, the first visible sign is the sea pulling back. The water recedes dramatically from the beach, exposing the seafloor for hundreds of meters, revealing stranded boats and fish flopping on dry sand. That retreat, the trough between 2 crests of the long wave, lasts for minutes and frequently draws curious onlookers toward the water's edge. Minutes later, the crest arrives. Tsunamis don't arrive like waves that break and pull back. They arrive like tides that rise abruptly and don't stop, pushing inland carrying water, sediment, vehicles, and structures. The destruction from the prolonged flooding, which can last for hours, far exceeds the destruction from the initial impact. Multiple crests arrive at intervals of 10 to 45 minutes, determined by the wavelength of the wave train generated by the earthquake. The second or third crest is frequently higher than the first, because interactions with coastal bathymetry and reflections off headlands and capes create patterns of constructive interference. Areas that survived the first wave can be destroyed by the second. This extended sequence behavior is one of the most deadly properties of tsunamis. Survivors who return to the coast too soon, believing the event is over, are killed by the subsequent waves. The state of sustained danger lasting for hours sets tsunamis apart from virtually every other coastal phenomenon. Modern warning systems integrate multiple data sources. Seismic networks that detect earthquakes within seconds, DART sensors on the ocean floor that confirm tsunami generation, and computational models that calculate arrival times and projected heights at different coastlines. The Pacific System, operated by NOAA, was built after the 1946 Hawaiian tsunami and progressively expanded. After 2004, construction of an equivalent system in the Indian Ocean began. Today, these systems can issue reliable warnings with minutes to hours of advance notice, depending on the distance between the affected coast and the epicenter. Communities close to the epicenter have very narrow windows, sometimes less than 15 minutes, requiring immediate evacuation protocols based on natural signs, without waiting for official confirmation. Community preparedness has proven just as important as technology. On the island of Simulu, close to the epicenter of the 2004 tsunami, almost none of the 75,000 residents died, despite being the first ones hit. The population had preserved an oral tradition called smung, passed down after a historical tsunami in 1907, which taught that shaking ground and a retreating sea meant running for the hills immediately. Without electronic alerts, without time to wait for official information, cultural memory saved an entire population. Contrast that with tourist areas in Thailand during the same event, where visitors unfamiliar with the natural warning signs walked toward the beach to look at the retreated sea, and were killed by the crest that followed minutes later. The same ocean that contains oxygen-free zones where nothing aerobic survives, that trapped plastic at the deepest point before humans arrived, that destroyed the Titan in milliseconds and remains invisible across 3/4 of its extent, can mobilize enough energy to kill more than 200,000 people in a single day with waves generated 5,000 kilometers away. The scale of ocean phenomena consistently exceeds the human capacity to intuitively anticipate them. Invisible pressure, chemically lethal zones with no sensory signal, contamination that preceded exploration, and seismic energy that crosses entire oceans silently only to become a wall of water at the shore. Every aspect of the ocean reveals a system of magnitude and complexity that humanity has barely begun to understand, even as it transforms it at an ever-increasing pace. If the pressure doesn't kill you, the heat might. Scattered across the ocean floor along mid-ocean ridges, hydrothermal vents expel superheated water at temperatures lethal to any organism not adapted to them. Fluid temperatures can reach 400 degrees Celsius or higher, but don't boil under the extreme pressure of the deep ocean. At 400 degrees Celsius and the pressure corresponding to 3,000 meters of depth, water becomes a supercritical fluid, neither liquid nor gas, that dissolves metals and reacts chemically with any material it contacts. As it emerges from a vent, the fluid at 400 degrees Celsius meets seawater at 2 degrees Celsius within a matter of centimeters. The temperature gradient across less than 1 meter is 398 degrees Celsius. No human biological system survives that gradient, but Pompeii worms and chemosynthetic bacteria inhabit exactly that boundary, in a demonstration that the definition of habitable depends entirely on who is trying to inhabit it. To understand why water at 400 degrees Celsius doesn't boil on the ocean floor, you need to understand what determines the boiling point of any liquid. At 100 degrees Celsius at sea level, water molecules accumulate enough kinetic energy to escape the liquid phase and become vapor, but only because the atmospheric pressure exerted on the surface of the liquid is 1 bar. Increasing the pressure raises the boiling point. At 10 bars, water boils at 180 degrees Celsius. At 100 bars, at approximately 310 degrees Celsius. At 3,000 meters of depth, hydrostatic pressure exceeds 300 bars. Under that compression, water molecules are kept forced into the liquid phase, even at temperatures that would vaporize any ordinary container at the surface. The physics that seems extraordinary is just thermodynamics applied to extreme conditions. Above a specific threshold of simultaneous temperature and pressure, called the critical point, the distinction between liquid and gas disappears. For pure water, that point is 374 degrees Celsius and 221 bars. For salt water with the typical salinity of hydrothermal fluids, the critical point shifts slightly higher, to around 407 degrees Celsius and 298 bars. Above these conditions, the fluid exists in a supercritical state. It is neither liquid nor gas, but an intermediate phase with properties of both. Supercritical fluids have a density similar to liquids, but viscosity as low as gases. They move through rocks and fissures with ease, carrying dissolved metals in concentrations impossible in ordinary water. It is precisely in this state that hydrothermal fluids circulate through the oceanic crust before emerging from black smoker chimneys. Hydrothermal vents are found mainly along mid-ocean ridges, underwater mountain ranges that circle the globe for more than 65,000 kilometers, comparable in total extent to the largest continental mountain systems combined. Along these ridges, tectonic plates pull apart, creating fissures through which magma emerges and seawater penetrates. The water descends through cracks in the crust, heats progressively in contact with igneous rock near the magma, dissolves minerals and metals from the rock, iron, copper, zinc, manganese, trace amounts of gold, and rises back up driven by density differences, emerging from chimney openings at temperatures that can exceed 400 degrees Celsius. Upon meeting the cold, oxygenated seawater of the immediate surroundings, hydrothermal fluids precipitate their dissolved minerals almost instantly. Metal sulfides, mainly pyrite, chalcopyrite, and sphalerite, form within milliseconds and accumulate around the chimney opening, building cylindrical structures called black smokers. These structures grow at rates of up to 30 centimeters per day under favorable conditions, reaching heights of 20 to 40 meters before collapsing under their own weight. The precipitated material is literally mineral purified by the geothermal process. Some deposits accumulated over decades contain concentrations of copper, zinc, and cobalt higher than many commercially exploited deposits on land. The Pompeii worm, Alvinella pompejana, inhabits tubes built on the side walls of hydrothermal chimneys in the eastern Pacific. About 10 centimeters long and covered with bacterial filaments that form a thick layer on its back. The worm positions its posterior end inside the tubes where temperatures can reach up to 80 degrees Celsius, while its head is exposed to the cooler surrounding water at temperatures of 20 to 25 degrees Celsius. The thermal gradient the animal is subjected to, dozens of degrees across its own body, is the most extreme tolerated by any known multicellular animal. Research with live organisms in pressurized aquariums showed that temperatures above 50 degrees Celsius for extended periods are lethal. Below that, the worm not only survives but thrives in an environment that would destroy any human tissue within seconds. The Pompeii worm's survival strategy combines behavior, biochemistry, and symbiosis. Rhythmic movements in and out of the tube circulate cooler water around its body, actively regulating temperature. Collagen, the structural protein that forms connective tissue, underwent evolutionary modifications that allow stability at temperatures where human collagen irreversibly denatures. The bacteria coating the worm's back are thermophilic, capable of operating at temperatures that would kill any mesophilic microorganism, and may act as biological insulation that moderates the heat at the posterior end. Each of these adaptations represents an independent evolutionary solution to the same problem: surviving where temperature kills. Beyond Pompeii worms, hydrothermal ecosystems harbor surprising diversity. Giant red tube worms, Riftia pachyptila, grow without a mouth or digestive system, depending entirely on chemosynthetic bacteria that inhabit a specialized internal organ called the trophosome. These bacteria oxidize hydrogen sulfide, the same toxic gas found in sewage and volcanic gases, to produce energy that feeds the worm. Blind shrimp, octopuses adapted to permanent darkness, thermophilic barnacles, and pelagic fish that visit the nutritionally enriched zone round out communities that function without a single particle of solar energy. The entire energy chain comes from Earth's chemistry, not from sunlight. The discovery of hydrothermal vents in 1977 by the submersible Alvin at the East Pacific Rise transformed biology in ways that go beyond simply finding new organisms. It demonstrated that complex life is possible without photosynthesis, and therefore without sunlight as a primary energy source. This dramatically expanded the number of environments in the universe where life could potentially exist. Icy moons like Europa, with subsurface oceans and possible hydrothermal activity on their floors, became plausible candidates for harboring life. Early Mars, with active volcanism and liquid water, could have sustained chemosynthetic ecosystems. The oceanic hydrothermal vent isn't just a biological curiosity. It is a concrete scientific argument about the potential distribution of life throughout the cosmos. The fluid at 400 degrees Celsius emerging from black smokers carries one final remarkable characteristic. It is extremely acidic. Sulfuric acid and hydrochloric acid form during circulation through magmatic fluids, dropping the pH to values between 2 and 4, comparable to human stomach acid or concentrated vinegar. The combination of lethal temperature, extreme acidity, crushing pressure, and the total absence of sunlight defines the environment of hydrothermal vents. Each of these variables, on its own, would kill any unprotected human being within seconds. All of them together would make any human visit technically impossible without protection equivalent to that of a spacecraft. And yet, in this environment that pushes past every limit human biology knows, worms with bacteria on their backs build tubes, reproduce, and thrive, redefining the boundaries of what life can be. Even before diving, the ocean presents its first threat right at the surface. Waves that appear without warning and reach twice the height of the surrounding swells. Rogue waves are unpredictable and can appear unexpectedly from directions that don't match the prevailing wind or waves. Most witnesses describe them as walls of water due to their unusually deep troughs. Between 1969 and 1994, rogue waves were responsible for the complete sinking of 22 supertankers, often with their entire crews. The first instrumental measurement of a rogue wave was the Dropner wave, a 25.6-meter monster recorded in the North Sea on January 1, 1995. In September 1995, the cruise ship Queen Elizabeth II encountered a 29-meter rogue wave during Hurricane Luis in the North Atlantic. The captain described it as a great wall of water. It looked like we were heading for the white cliffs of Dover. In December 2022, a rogue wave struck a cruise ship in the Antarctic Ocean, killing 1 passenger and injuring 4. By scientific convention, a rogue wave is defined as any wave whose height exceeds at least twice the significant wave height of the surrounding sea. Referred to as HS, calculated as the average of the top third of measured wave heights over a given interval. If the sea is running with an HS of 12 meters, any wave above 24 meters qualifies as a rogue wave. That definition reveals what makes the phenomenon so terrifying. It's not just the absolute height, but the contrast with the immediate surroundings. A ship designed and crewed to handle 12-meter waves encounters a 25-meter wave with no warning, no time to maneuver, coming from an unexpected direction. Classical statistical ocean models predicted this should happen extremely rarely, once every 10,000 years at any given point. Reality turned out to be far more frequent. The Dropner wave, recorded on January 1st, 1995 at the Norwegian Dropner S oil platform in the North Sea, changed oceanography. A downward-pointing laser sensor installed on the platform structure 18 meters above mean sea level recorded, at 3:24 p.m. Universal Time Coordinated, a wave with a maximum height of 25.6 meters, while the surrounding waves had an HS of approximately 12 meters. The wave was more than twice as tall as its neighbors. The platform sustained minor damage, confirming the sensor reading. Before that record, scientists dismissed sailors' accounts of monstrous waves appearing out of nowhere as exaggeration or maritime folklore. The Dropner was the first instrumental proof that the phenomenon was real physics. 9 months after the Dropner, on September 11, 1995, the Queen Elizabeth II was sailing 200 miles off Newfoundland, trying to avoid Hurricane Luis. Captain Ronald Warwick, a 30-year veteran of transatlantic crossings, had sent passengers to their cabins and altered course. At 4:10 in the morning, a wave emerged from the darkness off the bow. The crest of the wave was at eye level from the bridge, approximately 29 meters above the waterline. Warwick described the sight as looking straight at the white cliffs of Dover. The wave broke over the bow with a force that shook the entire ship. A second subsequent crest tore a mast from the forward deck. No one died, but the incident was documented with technical precision in the Marine Observer, one of the most detailed accounts of a rogue wave ever recorded by an experienced captain. The physics that generates rogue waves is still the subject of active research, but the main mechanisms have been identified. The first is linear focusing. When waves coming from different directions meet in phase, crests coinciding with crests, their amplitudes add together constructively. In the open ocean with multiple crossing wave systems, this coincidence occurs sporadically with enough amplitude to create a wave far taller than those around it. The second mechanism involves nonlinear interactions described by the nonlinear Schrödinger equation. Waves of similar wavelengths can transfer energy between each other in a way that concentrates amplitude into a single wave while the neighbors weaken. Strong ocean currents, such as the Agulhas Current off the coast of South Africa, also focus the energy of waves traveling against or at an angle to the flow. The historical tragedy that drove decades of scientific research into rogue waves was a series of unexplained sinkings between the 1960s and 1990s. Supertankers vanished in the open ocean without a mayday call, without survivors, in severe but not exceptional weather. The German ship München sank in the North Atlantic in December 1978 with all 36 crew members on board. Only debris was found. Analysis of the structural supports of the recovered lifeboat David showed metal deformation consistent with the impact of an extremely high-energy wave at 18 meters above the waterline. No open-sea wave should have reached that height under moderate sea conditions. The München was the first case where the rogue wave hypothesis was seriously considered as the probable cause. The European MaxWave project, launched in 2000 and completed in 2003, used radar data from the European Space Agency's ERS-1 and ERS-2 satellites to carry out the first global census of rogue waves. Within 3 weeks of satellite data, researchers identified 10 individual waves exceeding 25 meters in different parts of the world's oceans. Extrapolating to the full year and across the entire ocean surface, the actual frequency of rogue waves was dramatically higher than classical statistical models had predicted. One platform in the Goma oil field in the North Sea recorded 466 rogue wave events over 12 years, more than one per week on average. The conclusion was unambiguous. Rogue waves are not statistical rarities. They are routine ocean events that naval engineering had simply ignored. The Viking Polaris was sailing through the Drake Passage, the most treacherous stretch of ocean on the planet, between Antarctica and South America, on November 29, 2022, carrying 378 passengers bound for Ushuaia, Argentina. At 10:40 p.m., the ship's hull was struck on the starboard side by a wave that Viking Cruises classified as a rogue wave, shattering a series of windows in the Deck 2 cabins. The freezing water of the Antarctic Ocean flooded the compartments, slamming furniture against doors and trapping passengers. One passenger died from injuries caused by broken glass, for others were injured. The geographical irony is thick. The Drake Passage was named after the privateer Francis Drake, whose ship was pushed southward by a storm in 1578. The same ocean that continues, for 144 years later, to exact its toll from those who cross it. Ship construction has evolved little to address rogue waves between the era of the disappearing supertankers and today. Ships are designed to withstand waves with a maximum height determined by classical statistical models, which underestimate the actual frequency of rogue waves. The discovery that these events are more common than previously believed demands a revision of construction standards, but changing international naval engineering norms is a slow and politically complex process. Monitoring systems based on onboard radar, forward-facing cameras, and algorithms for early detection of anomalous waves are being developed, but none can create enough time for effective maneuvering when a 25-meter wave emerges, less than a minute away in the darkness of a stormy ocean. The ocean that destroys submarines with pressure, that harbors chemically lethal zones without any sensory signal, that carried plastic to the deepest point before humans arrived, that moves enough energy to kill 227,000 people with a single underwater earthquake, and that heats water to 400 degrees Celsius without letting it boil. That same ocean projects 25-meter waves that appear without warning out of nowhere, in the dark, at a speed that allows no human reaction. Every one of these phenomena emerges from the same physical system, a water column of varying depth, subjected to pressure, temperature, gravity, winds, and tectonic forces. The ocean is not a collection of separate dangers. It is an integrated system where energy transfers between forms with total indifference to the presence or intentions of any observer. In the zone where humans actually enter the ocean, the coastal surf zone, the main threat has no teeth, no body, and no visible form. Rip currents are narrow channels of water that flow rapidly out toward the open sea, perpendicular to the shoreline, capable of dragging any swimmer regardless of their skill level. An Olympic swimmer cannot swim against a rip current moving at 2.5 meters per second. The speed physically exceeds the maximum swimming speed of any human in any stroke. In the United States, rip currents account for more than 80% of rescues performed by lifeguards on ocean beaches. In 2024, there were only 47 unprovoked shark bite incidents worldwide across all species combined, with 4 confirmed fatalities. Rip currents kill dozens of people per year in the United States alone. Invisible, formless, and without the reputation that sharks carry. A rip current forms when waves break continuously at the shore and push water toward the beach. That accumulated water needs to return to the sea and finds the path of least resistance. Points where the bottom bathymetry allows concentrated flow, such as gaps between sandbars, areas adjacent to structures like jetties and piers, or natural breaks in the surf line. In that narrow channel, all the water accumulated by multiple waves escapes simultaneously, creating a one-way current of surprising speed. Typical rip currents flow at 0.5 meters per second, already enough to make it difficult for weak swimmers to get out. The most intense ones reach 2.5 meters per second, exceeding the maximum sustainable speed of any human swimmer, including Olympic athletes. Invisibility is the most lethal property of rip currents. Unlike sharks, which trigger instinctive fear, or large waves, which are visually obvious, a rip current can paradoxically look like a calm area. The outgoing flow suppresses the waves that would normally break at that point, creating a strip of water that appears smoother and more peaceful between areas of active surf. To someone without specific training, that appearance can seem inviting, an easier access corridor to the sea. Beaches without proper signage and without lifeguards offer no protection against this perceptual trap. The first sign many victims notice is being pulled away from shore without being able to swim back. The instinctive response of swimming directly against the current toward the beach is the reaction that kills. A panicking swimmer trying to fight their way against the flow makes no progress. They stay in place while burning through energy rapidly, until accumulated muscle exhaustion results in an inability to stay at the surface. The current, meanwhile, doesn't stop. It has no intent, no preferences, and doesn't give way to human effort. The correct protocol is counterintuitive. Swim parallel to the shore, crossing the current laterally instead of fighting it head-on, until you exit the narrow channel, and only then return to the beach at an angle. For someone in a panic who has never heard this instruction, executing it is nearly impossible without prior training. In the United States, the Life Saving Association estimates that rip currents cause around 100 drowning deaths annually on the country's beaches. The exact number is hard to pin down because the cause of drownings isn't always rigorously documented. The more carefully tracked average from NOAA indicates approximately 71 deaths per year between 2013 and 2022. Either way, the contrast with sharks is overwhelming. In 2024, an exceptionally quiet year, according to the International Shark Attack File from the Florida Museum of Natural History, there were only 47 unprovoked attacks worldwide, resulting in 4 confirmed deaths. Rip currents kill more people in a single American state in a single summer than sharks kill worldwide in typical years. The wildly disproportionate reputation of sharks compared to rip currents is a direct product of how media and culture process risk. Sharks are animals with teeth, their own behavior, a menacing appearance. They trigger fear circuits evolutionarily calibrated to respond to predator threats. Rip currents are abstract physical phenomena, invisible, without a narrative. The movie Jaws from 1975 caused a measurable drop in beach attendance across the United States during that summer. No movie about rip currents has ever had a comparable effect on human behavior. Even though rip currents consistently kill more Americans per year than lightning, hurricanes, and tornadoes combined, according to data from the National Weather Service. Identifying a rip current before entering the water is possible with specific visual training. Signs include a strip of water with a different appearance from the surrounding waves, often more turbid, with a slightly different color from suspended sediment, an absence or break in the regular wave pattern in one specific section of the beach, foam, seaweed, or floating debris moving toward the sea in a relatively straight line, and different surface agitation, with a pattern of smaller ripples instead of the defined crests of the surf zone. Watching the beach for a few minutes from an elevated angle before entering the water, from the top of dunes or structures, significantly improves detection. On beaches without lifeguards, that habit can be the difference between life and death. The full scale of the rip current problem globally is hard to quantify precisely because drowning data rarely specifies the cause. In Australia, where statistics are tracked more rigorously by organized lifeguard services, rip currents were recorded as causing more deaths than wildfires, floods, cyclones, and shark attacks combined, according to a 2013 study. Beaches without lifeguard coverage have dramatically higher drowning rates. The probability of drowning in front of a trained lifeguard station is calculated at approximately 1 in 18 million. Most rescues happen outside monitored zones, where no one was present to detect the danger before the swimmer entered the water. Rip currents illustrate a broader principle about how humans assess risk in the ocean environment. The visible danger, with a recognizable shape and behavior, gets attention and preventive resources, shark warnings, swimming bans after sightings. The invisible danger, formless and without a narrative, goes largely ignored until a specific victim makes it briefly concrete. Oxygen minimum zones have no distinct appearance. Rip currents can look like calm water. Microplastics are imperceptible. Every one of the ocean's most prevalent dangers shares the property of being chemically, physically, or hydrodynamically invisible to the human sensory system. Calibrated for terrestrial environments over millions of years of evolution under conditions that didn't include the ocean as a regular habitat. The ocean that harbors sharks, organisms with 450 million years of evolutionary history, predating the first terrestrial forests, keeps those animals far less lethal to humans than a water flow that nobody can see. Sharks kill 4 people in unprovoked attacks worldwide in an exceptional year. Rip currents kill the same number in a single summer morning on a popular beach without lifeguards. The gap between cultural fear and statistical risk has rarely been as wide as in this comparison, and that gap costs lives systematically, every summer season, on every inhabited ocean coastline on the planet. The ocean covers 361 million square kilometers. At any point across that territory, an unprotected human being has a survival window ranging from minutes to hours before hypothermia, pressure, drowning, or chemical poisoning ends the process. Pressure destroys submersibles in milliseconds at 3,800 meters. The floor has water at 400 degrees Celsius that doesn't boil. Oxygen-free zones expand without warning. Tsunamis invisible in the open ocean become 30-meter walls at the shore. Rogue waves of 29 meters appear with no forecast. Rip currents outrun the top speed of any human swimmer, and 74% of that environment's floor has never been mapped in high resolution. The same ocean that destroyed OceanGate's Titan in milliseconds, that has superheated water at 400 degrees Celsius on its floor, that already has plastic trash scattered across the most inaccessible points on the planet. That ocean absorbs 25% of human CO2, regulates the climate of every continent, sustains the largest food chain on the planet, and is the reason Earth's atmosphere still has enough oxygen to breathe. Every phenomenon described throughout this narrative is an expression of a single physical system. The ocean as a dynamic reservoir of mass, energy, and chemical compounds in constant redistribution. The pressure that destroyed the Titan in milliseconds is the same water column that regulates the planet's temperature by absorbing heat. The 400 degrees Celsius water from hydrothermal vents is the same geothermal process that from Earth's interior transfers essential minerals to the ocean floor, where chemosynthetic organisms convert them into biomass. The rip currents that drag swimmers are coastal miniature versions of the same currents that carry tropical heat to polar latitudes. Every lethal aspect of the ocean and every vital function it performs emerge from the same physics, the same chemistry, the same system. Phytoplankton, photosynthesizing single-celled organisms that drift in the sunlit surface layers, produces approximately half of all the oxygen in Earth's atmosphere. Not tropical forests, not land plants. Organisms invisible to the naked eye, dispersed across the entire ocean surface, collectively performing photosynthesis on a scale that surpasses any terrestrial ecosystem. This process existed for billions of years before any plant colonized dry land, and progressively transformed the primitive atmosphere, rich in CO2 and methane, into the nitrogen-oxygen mix that allows aerobic respiration. Without the ocean, no phytoplankton. Without phytoplankton, no atmospheric oxygen. Without atmospheric oxygen, none of the aerobic life forms that inhabit the planet today, including all mammals, all birds, all reptiles, and all humans. The ocean carbon cycle operates on multiple timescales simultaneously. At the surface, phytoplankton absorbs dissolved CO2 during photosynthesis on a scale of days. When those organisms die, they sink carrying carbon to the ocean floor, a process called the biological carbon pump, where part of it is remineralized by bacteria over the course of weeks, and part is deposited in sediment and remains sequestered for millions of years. The ocean floor accumulates, over geological eras, thick layers of organic carbon and carbonate that constitute a colossal reservoir, far larger than all terrestrial biomass and the entire atmosphere combined. Disruptions to this cycle, caused by acidification that dissolves carbonates or by warming that alters circulation patterns, directly affect the ocean's capacity to regulate atmospheric CO2 concentrations on timescales relevant to human civilizations. The Atlantic Meridional Overturning Circulation, the system of currents that moves warm surface water northward and cold deep water southward, distributes heat with an efficiency that no artificial heating system could replicate. The heat transported by this current is equivalent to approximately 1 million power plants operating continuously. Without this redistribution, polar regions would be drastically colder and the tropics drastically hotter. Rainfall patterns would depend on entirely different evaporation and condensation dynamics. No agricultural civilization would have developed the way it did over the past 10,000 years without the moderate climate that this current system provides, and whose stability is being tested by current warming in ways that models still cannot predict with sufficient precision. The central irony of this entire narrative is that the ocean is simultaneously the most hostile environment to unprotected human survival and the most essential system for maintaining the conditions that make Earth habitable. Pressure that implodes structures, chemically lethal zones, currents that outpace Olympic swimmers, rogue waves without warning, invisible tsunamis. Every danger is a property of the same system that absorbs CO2, regulates temperature, produces oxygen, and distributes heat across continents. It is not possible to separate the vital functions from the lethal dangers because both emerge from the same physical and chemical properties. The ocean is not dangerous despite being essential. It is essential for the same reasons it is dangerous, because it stores and transfers energy on scales that completely transcend any human scale. Only 27.3% of the ocean floor had been mapped to modern standards as of 2025. The same year that percentage was announced, submarine permafrost in the Arctic continued thawing, releasing methane accumulated over thousands of years. Plastic deposited in Challenger Deep remains intact, unchanged, waiting. Hydrothermal vent ecosystems sustain life under the most extreme conditions the planet offers. A reminder that life finds a way wherever energy and chemistry allow. Oxygen minimum zones are expanding in chemical silence. The ocean that destroyed the Titan in milliseconds holds, in the regions we have yet to map, processes that determine whether the planet remains habitable for generations who will never know the name of any of these phenomena, but who will depend on all of them to exist. Every journey into the ocean begins in the same coastal zone, where rip currents drag unsuspecting swimmers out toward the open sea. That transition, from sand to shallow water, from shallow water to the surf zone, from the surf zone to the open ocean, is the same gradient that separates the human environment from the ocean environment. Every additional meter of depth imposes pressure, temperature, and chemical composition progressively further from what the human body has tolerated throughout its evolutionary history. On the 10th floor of a building, the pressure is the same as at the surface. At 10 meters of depth in the ocean, it is already double. At 3,800 meters, it is 380 times greater. At 10,935 meters, in Challenger Deep, where plastic trash quietly waits, it is more than 1,000 times greater. And the only human visitor to reach that point before the trash was Jacques Picard, in 1960, protected by a solid steel sphere weighing 150 tons. The ocean receives everything we deposit in it and returns nothing that hasn't been, in some way, transformed. The ocean began this story as the abyss that destroyed the Titan in milliseconds, and ends it as the system that makes it possible to breathe the air in this sentence. Between those two extremes, every topic revealed the same truth from a different angle. A system of scale and complexity that humanity has barely begun to understand, has already profoundly transformed, and absolutely depends on plastic at the deepest point before any human expedition arrived. Submarine permafrost thawing with the potential to release methane that amplifies warming that accelerates the very thaw. Oxygen-free zones expanding in chemical silence. Hydrothermal vents sustaining life under the most extreme conditions the planet offers. A reminder that life finds a way wherever energy and chemistry allow. The ocean does not need humans to exist. Humans, however, could not exist without it.